But there's no microphone here. No, not on the mic, but none of these are working. No. Okay, we can start. I cannot wait for no, that one I cannot use. Just open it there, yeah. Okay, today we don't have any mic. If you want to come closer, then sit closer if you want to hear. Today, my lecture is about thermoregulation, and these are the learning objectives for this lecture. And the first question is, what do we define as body temperature? We have one here, the core of the body. In the core of the body, where all organs are, they have always a constant temperature of 37 degrees Celsius. Okay? Core temperature is always constant, 37, as you see here. But the peripheral part of the body, legs and arms and the skin, it has variable temperature. The temperature that you measure on the skin depends on the ambient temperature. Ambient temperature means outside temperature. And also it depends on location. At what location you measure and by which ambient temperature you measure. So this peripheral part of the body has a variable temperature, as you see here, dependent on location and dependent on ambient temperature. And because they are too many, then we average all those kind of skin temperature to a mean skin temperature, what you see here. And mean skin temperature and body temperature and core temperature are averaged together as mean body temperature. Okay? Mean body temperature is an average of core temperature and mean skin temperature. Okay. And now, as a physician, always you need to measure the core temperature. For example, if your patient has fever, then you have to measure the core temperature because the core temperature changes. And it means the closer you are to the core of the body, the better would be temperature measurement. Yes? And therefore, rectal temperature measurement is better than oral measurement, and that is better than axillary measurement. Because the closer to the core of the body, the more accurate is the measurement of core temperature. Okay, I told you that the core temperature is constant, but it shows some variability. And the variabilities are shown here. One, we call it circadian variability. You see during the 24 hours of the day, the temperature changes a little bit. At the early morning hours, 6 o'clock at the morning, you have the lowest body temperature. At 6 o'clock at the evening, you have the highest body temperature. And the difference could be half degree until 1 degree Celsius. And also there is a long period variability, and that is, you see here the body temperature, the red curve, post-ovulation, and the blue one, peri-ovulation. After ovulation, the body temperature jumps by 0.2 degree. And in the past, historically, if you consider it, the people used this method to avoid pregnancy. And if you use that method for avoiding pregnancy, you have to measure body temperature always at the same time. You cannot measure the body temperature once here and another time here, then you make mistake. The body temperature must be measured always at the same time. That has been mostly by normal population the mistake that they made, because they measured them, for instance, once the temperature at the morning, and then next day at the evening and said, oh, that is post-ovulation. And that is, you must measure the temperature always at the same time. Okay. And now what we do in this lecture, the question is, what determines the body temperature? Body temperature is resulting from a balance between heat production in the body. You know, by metabolism, we produce heat in the body, and heat dissipation from the body to the environment. If heat production and heat dissipations are equal, then the body temperature remains constant. If heat production is more than heat dissipation, then the heat will be stored in the body and it causes a rise in body temperature. And the opposite also the case. So what we do in this lecture hour, first we learn the mechanism of heat production, then we learn the mechanism of heat dissipation, and if they are equal in a time, then the body temperature is constant. And if they are not equal, then they change the body temperature, okay? And first, we look at the mechanism of heat production. For example, by physical work, we produce heat. For all physical work, 75% of the energy which is used for the work is transmitted to heat. Only 25% is transmitted to work. For example, if I lift it up here, from 100% energy that I used, 25% were used to lift it up, but 75% become heat in my body. So, and if you go by internal work, so for example, heart is working, liver is working, all glands are working. At the end, all the energy which is used by those processes, you learn ATP is used by those processes, at the end you get heat. The last form of the energy in the body is heat. Therefore, you can say all this internal work at the end is 100% heat, is transferred to heat. And then we have by thermoregulation, if it is winter and we are shivering, then we produce heat. And that is heat production, for example, by shivering, and 100% is transmitted to heat, the energy is transmitted to heat. And by non-shivering thermogenesis, also you produce heat. Particularly the babies, they have brown fat, and brown fat is metabolized to produce heat if the environment is cold. The other things that you should pay attention, you see here, normal heat that we produce is basal metabolic rate. Do you know basal metabolic rate? It is about 1,700 kilocalorie per day or something like that. And that basal metabolic rate can increase 12-fold by physical work. And it can increase 5-fold by thermoregulation, and can increase 2 to 3-fold by non-shivering thermogenesis. You see here, there is a very high capacity to increase the heat production if it is needed, okay? If it is cold, then we need to produce more heat, although the body has the possibility to do it. And now, before I start with the mechanism of heat dissipation, I want to bring you an example to see if we, at basal metabolic rate, at BMR, if we have no heat dissipation, okay, no heat loss, all that heat will be stored in the body, and then it will rise the temperature of the body. And we want to see how fast the body temperature will rise and to how much. And that is shown in this example. Our heat capacity of the body is 60 kilocalorie per 1 degree Celsius. Why that? Because we are water. 70% of us is water. If you know the definition of kilocalorie from school, is the amount of the heat or energy that you add to 1 liter water to bring its temperature, to increase its temperature by 1 degree. Although 1 liter, 1 degree is a kilocalorie. And we are 6 liter water, and therefore 60 kilocalories would raise our body temperature by 1 degree. And how much kilocalorie we produce? 1.2 kilocalorie per minute. How long does it take to get 60 kilocalorie? 1.2 after 50 minutes. 50 times 1.2 is 60. It means every 50 minutes, our body temperature will rise to 1 degree Celsius if there is no heat dissipation. And you have a body temperature of 37, and by 33, 34, you die, then it takes actually 7 times 50 minutes to kill you if there is no heat dissipation. And now look, if we, at the maximal metabolic rate, if we work very hard, then we produce 11 kilocalorie per minute, and it takes 5 minutes to have 60 and raise the body temperature by 1 degree. Every 5 minutes, your body temperature will rise to 1 degree if there were no heat dissipation during maximal work. It means in 6-7 minutes you will die. You see how efficient that is, how important it is that we have heat dissipation, that we dissipate heat to the environment. And now we study by which mechanism do we dissipate heat to the environment. First of all, you must know that the heat is produced in the organs within the body. And from organ directly, the heat cannot be passed to the air outside, because there are something between my heart and here, the air outside. Therefore, this heat produced in the organs must be transported to my skin, must warm up the skin, and after the skin is warmed up, then the heat will be transferred from skin to the environment. And which transport system bring the heat from the core of the body, from inside of the body to the skin? That is the skin blood perfusion, blood flow to the skin. And you see that the heat transport from core of the body to the skin is happening here. This transport is happening by blood flow to the skin. Blood flow, all the heat must be transported by blood to the skin. And now after our skin becomes warm, then we dissipate the heat from skin to the environment. And for that, which type of mechanism do we have? We have these mechanisms. Conduction and convection, and then radiation of the heat, and then evaporation. These 3 mechanisms. If you separate these from each other, then 4 mechanisms. And by conduction and convection, we evaporate, or we dissipate about 20% of the heat. By radiation, we dissipate about 50% of the heat. You see, nobody think about radiation. That is the most important factor for heat dissipation, radiation. Every warm surface radiates heat to a cold surface. If my body is warmer than this wall, my body radiates heat to the wall. And then the rest of this, 30%, is the heat loss is caused by water vaporization, also by water vapor. Okay? And that is happening by breathing, because the air that we inhale is dried air, and after we exhale it, it is humidified. Also by breathing, and also on the skin. Our skin, even it looks dry, but it is not dry. It is always water on the skin. The problem is, as the water comes on the skin, immediately it is vaporized, and therefore you don't see it. But it is happening continually. And now we go to the, and you see here the conduction and convection depends on insulating layers. Insulating layers, that it means what do we wear to insulate our skin, our body surface. And also by the insulating of air layer. You see here the heat loss from skin by conduction and convection. That is, yeah, one other thing that I want to tell you here, which is very important. These two mechanisms, conduction, convection, and radiation, depends directly on temperature difference between our skin and outside. If the outside temperature is higher than my skin temperature, then we gain heat by these two mechanisms. We cannot dissipate heat, we gain heat. It goes from outside into our body. The only mechanism that we can dissipate heat against a higher environmental temperature, that is water evaporation. And that is particularly important for you living in Saudi Arabia, because mostly the outside temperature is 40, 41, 42, and you cannot dissipate heat by those temperatures through conduction and convection and through radiation. You gain heat, and all that heat is dissipated from your body by evaporation of water. Okay? And we now look at the conduction and convection. You see, it is proportionate to what happens now? What? Come and goes? Also, you must really make a complaint to the dean that none of these lecture halls are working correctly. None of them. It is terrible. They have a very big office about, I don't know, quality of teaching, but they don't fix the problems which are in every lecture hall. It is always good on the paper. In reality, particularly, I'm sorry, this IT department, forget about it. Okay. And now if you go here, but you see that this transport is depending on temperature difference, and also depends on thickness of the insulating air layer. What does it mean? It means if I take my hand here, and then the air is directly in connection with my hand, the layer of the air which is directly on my hand is not moving too much. The higher I go, the movement of the air is more. If I have wind here, for instance, air condition blowing now, mostly it takes the layer here above. The last layer, which is on my skin, it moves also, but moves very much, very little. And that layer we call is insulating air layer. The thinner that insulating air layer is, the greater is the conduction. If the insulating air layer is larger, then the conduction of the heat is less. And also the thickness of this insulating air layer is important, and also the curve of the body is important. Why that? Because at part of the body which are curvy, also like curve, then the insulating air layer is very thin, and therefore the heat dissipation is greater. And that you experience by yourself. In the winter, normally where do you freeze? In your body, in the fingers, and nose, and ears, because they are very curvy. And then the insulating air layer is very thin, and heat dissipation is much higher at this region than at your body surface. The conduction is high. Yes, otherwise it will be not conducted to the outside. We give the heat by conduction and by convection. What is the difference by the two? Conduction means if I have my hand and there is no airflow at all there, then the heat will be transferred to the air by conduction. As soon as I have wind, which blow here, take the cold air, the warm air away and replace it by cold air. That is convection. Conduction you have if there is no air movement on the body, no movement. Convection if the air is moving, and always warm air is replaced by cold air. So, and now the other mechanism is radiation. As I told you, it is also depending on temperature difference. It goes in the power of 4. Every warm surface radiates to the cold surface. That is, you know also, if you sit in front of a fire, then you feel that front of you become warm. In the back, you don't become warm. If it were transmitted through the air, then it must warm you from all over. It is not transmitted by air, not transmitted by conduction and convection. It is transmitted directly from fire to your body surface. And also, if you stand in the sun, you realize it. That is by radiation. And then by evaporation. What does it mean? If we take 1 liter of water and we boil it until all liter of water is vaporized, then for that process we need 580 kilocalories. It means if we vaporize 1 liter of water on our surface, on our skin, then it takes 580 kilocalories from our skin, from our body. That is huge. You see, by 4 liters, you have 2,000 kilocalories. And then where it is happening by lung, as you know, dry air goes in, humidified air comes out, and also through skin. You see here that the evaporation from a skin surface is proportionate to partial pressure of water vapor. Partial pressure of water vapor, not temperature difference. Partial pressure difference of water vapor, and this partial pressure of water vapor depends itself on temperature. Okay, and now to understand it, we make an example. For example, we have our skin temperature is 35 degrees Celsius, okay? And then by 100% humidity of on the skin, and I told you, skin is always humidity at the skin is 100% all the time. Then by 100% humidity, the water vapor pressure at the skin would be 42 millimeter of mercury. Okay? That is what you read from tables. Temperature, water vapor pressure by 100% saturation. And then let's assume you have an ambient temperature of 40 degrees Celsius. You see, this temperature is much higher than 35. Then let's say if humidity would be 100%, then the water vapor pressure by this 40 degree would be 55 millimeter of mercury. Okay? By 100% humidity, 55. And you see this 55 millimeter of mercury is higher than 52. Then you cannot dissipate heat. Yeah, because the environment, the pressure is higher than on your skin. You cannot dissipate heat. But the point is, if the humidity is less, let's say 60%, the water vapor pressure would be 60% of 55. 60% of 55 is how much? 33 millimeter of mercury. And now you see this 33 is less than 42, and you can dissipate heat. Even the temperature outside is higher than your body temperature, but the water vapor pressure is here less than there because the humidity is not 100%. And you are lucky here in Riyadh, the humidity is 2-3%. And then it makes a huge difference that you can evaporate the water very easily. Pardon? I cannot explain again because I have no time. I must deliver the class to the next person. Sorry, ask the others, then they explain it to you. Okay, how the skin becomes humid. It must become humid to evaporate the water. And that is becoming humid by water permeability of the skin, and that permeability is 0.02 liter per hour on our skin. In a day, it is about 0.5 liter per day, the water that we evaporate from the surface. But if we start to sweat, then we can produce until 4 liters sweat in 1 hour. And imagine all this sweat will be vaporized. Every liter will make 580 kilocalorie. 4 liter, about 2,000 kilocalorie in 1 hour. The whole BMR will be dissipated in 1 hour if you have maximal sweating. So powerful is this mechanism, sweating for heat dissipation. But remember, if you are sweating and the sweat drops on the ground, that drop which fall on the ground doesn't contribute to thermoregulation. It is lost as water. It doesn't take any heat with itself because it must be evaporated to take the heat from the body. And also, if you are sweating and take something from the pocket and clean that very nicely, it is good for you. You are looking nicer, but it is very bad for your thermoregulation. That water has been secreted to be evaporated, to cool you down. And now you take it away, and therefore you will not cool down enough. So that water what comes on the surface must be evaporated to cool you down. Okay, and as I told you before, the transport of the heat from the core to the surface is by blood flow, cutaneous blood flow. And look how the blood flow can increase. The blood flow to underarm can increase 7 times. The blood flow to the hand can increase 30 times above normal. And the blood flow to fingers can increase 600 times more than normal. Okay? And why these areas increase more blood flow? Can you make the connection? They were the areas which were curvy and then could dissipate the heat better. Therefore, it makes sense to bring more blood there where the heat can be dissipated easier. Okay, and now if you look at the hand, in the hand, as you learned in anatomy, you have deep arteries and deep veins. And then also you have superficial veins. And now if you want to conserve the heat, for instance, it is winter, you don't want to dissipate so much heat, what do? Do you flow the blood through the deep venous system or through the superficial venous system? Through deep venous system, so that your skin doesn't heat up. If you want to dissipate more heat, then the blood flow increases through superficial venous system. And that is also what you know from yourself. By hot weather, if you look at your hand, you see the veins because they are filled with water, with blood. If it is cold, then you see no veins in your hand. Okay, that is what is happening. If you look at the finger, by ambient temperature of 35, you see by 35 is a warm temperature. You want to dissipate more heat. Yeah. What do? The blood will flow through superficial veins. They are the superficial veins. And therefore, the skin temperature remains high. And you see here the skin temperatures. The beginning of the temperature was 37, and they are not so much different than 37. But if you are exposed to a cold environment, 10 degrees Celsius, what the body does, you see that the blood flow through these deep venous system. The superficial venous system is not perfused with much blood, and therefore the skin temperature goes down, and to reduce the heat dissipation. You see the temperature, if you compare these temperatures, for example, to this, you see that the skin temperature is much lower, and therefore the heat dissipation is lower. So, and how the body regulate that now the cutaneous blood flow must, if it is warm, the cutaneous blood flow must increase and sweating must increase. Yeah. And if it is cold, the blood flow must decrease and you must start to shiver. How it is regulated? Everything is regulated by, not everything, the most part is regulated by sympathetic stimulation. If we have a cold environment, then the norepinephrine sympathetic fibers will be stimulated and they make vasoconstriction, as you know. And then the skin perfusion, blood perfusion decreases below 5% or to 5%. And mostly in these areas where the most heat is, the most heat is transferred to the environment. And if you are exposed to cold weather, then you to warm weather, then you must have vasodilation. And that is also done by sympathetic fibers, but they are acetylcholine and VEP containing fibers. Also the transmitter is acetylcholine and VEP, and they causes cutaneous vasodilation. And that increases the blood perfusion to skin to 95% or something like that. And also what remains is sweating. And you see that is also regulated by cholinergic fibers. Acetylcholine is the transmitter, and that and it is these fibers stimulate sweat secretion to cool down. Also, cholinergic fibers are stimulated to cool down. Norepinephrine fibers are stimulated to warm up. And warming up is also happening by shivering. Shivering doesn't happen through sympathetic activity. Shivering happens through alpha motor neurons, also motoric nervous system. And that is mechanism of heat production, for example. Okay, now we want to see how the body regulates the body temperature. Here, the body temperature is plotted against ambient temperature. And you see that the body temperature between an ambient temperature of 40 to 5 in this area, it is constant. The body temperature remains the same. It is horizontal. It means that the body temperature by environmental temperatures between 5 and 40 is fantastically regulated, very well regulated to a constant value of 37. If the environment becomes colder than 5 degrees, then you see that slowly our body temperature drops. And this reduction in body temperature, we call it hypothermia. And if the ambient temperature goes above 40, then our body temperature slowly increases. And that is what we call hypercapnia. So on this part, we have normothermia, not capnia, sorry, thermia. Normothermia, and that is well regulated in this range. And in both sides here, we get hypothermia and hyperthermia. Okay? And now we want to know how the body can regulate the body temperature in this range between 40 and 5. What is a very nice ambient temperature for us? That is here 25, 26 degrees Celsius. That is the most comfortable temperature that we call it neutral ambient temperature. Okay, T neutral is 25, 26. And now let's say the environment becomes colder. What happens now? If the environment becomes colder, if we do, the heat dissipation become more because the environment temperature decreases, then what we should do to keep the core temperature constant? We must produce more heat. Also, what we do is the heat generation increases. It increases so much that compensates for heat dissipation, so that the body temperature remains constant here. Okay, what happens with mechanism? What should happen with mechanism of heat dissipation? Should they increase or decrease if we want to warm up our body? They should decrease. But if you look at them, here the blood perfusion, and that is the sweating, they don't decrease in this range. Why? Because they are at their minimal value. You cannot go below minimal value. But now, if you look at this, what happens if the ambient temperature goes above 26? Here, then we must reduce the heat production. We cannot reduce this too much because it is at its minimum. And then, if it is not possible to reduce heat production, what do you do to dissipate more heat? You increase the mechanism for heat dissipation. That was blood flow to the skin and sweating. And see what with the blood flow happens. From this temperature, the blood flow increases to increase the heat dissipation. And after a temperature of 32, 33 here, then we start to sweat. You see here, by this temperature, blood flow becomes almost maximal, has no capacity more. Then we start to sweat. The sweating starts and it goes until 40 degrees. and compensate for increase the heat dissipation. One thing that you see here, look at the heat generation. The heat production also increased. Is that good for thermoregulation or not? It is not. It is counterproductive. But we have no other choice, because if the glands, if the sweating glands are working more, or the heart is working more to increase cardiac output, then they produce heat. And that heat comes in addition to basal metabolic rate, and we should dissipate by other mechanisms. Okay. In summary, you can say between 5 and 25 degree ambient temperature, the body temperature is regulated by shivering, by heat production. Between 25 and 35, by increasing skin perfusion, and between 35 and 40, by increasing sweat secretion. So, and now how does our body know what is the temperature to increase either thermal heat production, or decrease or increase sweating or blood perfusion? First, the body must know how is the body temperature. And we have in hypothalamus two regions, anterior hypothalamic region and posterior hypothalamic region. These two regions of hypothalamus do two things. One is they dictate the body, the set point temperature for body. It means by us normally, this hypothalamic region tells the body, regulate everything to body temperature 37. That is in order. And that temperature we call set point temperature. The temperature is set at 37 degrees Celsius by hypothalamus. And the other job of hypothalamus is that you have in these regions receptors. You have cold receptors and you have warm receptors. They measure the temperature. If the temperature is low, they heat up the body. And this anterior hypothalamus is called also cooling center. Cooling center. If they measure a high temperature, this center then does everything to cool the body down. And it means skin vasodilation and sweating to bring the temperature down. If it is, they measure a cold temperature, then they want to warm the body. And that is the job of posterior hypothalamus. Therefore, we call it warming center. It was cooling center. This one is warming center. What does it do? It produces shivering, and also it makes skin vasoconstriction. And by those processes, heats up the body. Okay? Not only these receptors in hypothalamus, we call it central receptors, thermoreceptors. We have also a skin thermoreceptors, warm receptor and cold receptor also in our skin. And they are shown here. You see the core temperature is measured by central receptors, thermoreceptors, and the skin temperature is measured by skin thermoreceptors. And you see here, central thermoreceptors, skin thermoreceptors. And these signals from these receptors are sent to a control center. Control center get the information from these receptors. 90% the information coming from central, and 10% from peripheral, from skin receptors. And also the center receive information from hypothalamic temperature set point. what is the order of hypothalamus to set the temperature, body temperature at 37, 39. For instance, 39 could be by fever. So, and also it gets information from temperature set point from skin. All this information are integrated and a response is produced to change the temperature. And that response goes to vasomotoric activity of a skin to increase the perfusion if it is cold, if it is warm, to decrease the perfusion if it is cold. It goes to sweating glands, that if it is warm, sweating starts, and it goes to muscles, that if it is cold, the shivering starts. Okay? So, and in those correct the temperature, and this corrected temperature is again measured by these thermoreceptors, and that is the feedback system that you get there for regulation of body temperature. Okay, and now assume that you have a body temperature which is higher than normal body temperature. For example, your set point temperature is here, and your body temperature is higher than set point temperature. Okay? Here, the difference is higher. What should the body do in this case? Should warm up the body or cool the body down? Cool down. And everything that you know is happening there. You see here, heat generation must reduce, heat dissipation increases, although skin perfusion increases, and sweat secretion increases to cool the body down. So, and that brings the body temperature closer to set point temperature. The opposite is true if your body temperature is lower than set point. Although here is the set point temperature, and that is the body temperature is lower. Now, the body should be warmed up. Which mechanism do you use? You increase the mechanism for heat generation, and you decrease the mechanism for heat dissipation, which is you reduce skin perfusion and you reduce sweating. Very simple. That is the way that the body regulates the whole thing. And now a few definitions. Definition of hypothermia. I told you, if the body temperature falls down below 37, then you get hypothermia. If it goes up above 37, you get hyperthermia. But what you should remember or know is that by hypothermia and also by hyperthermia, the set point temperature is normal. The set point temperature of hypothalamus is normal 37. Hypothalamus tells the body regulate at 37. The body cannot do it because its mechanism are overwhelmed. The difference is simply too much that the body cannot regulate, and therefore the body temperature decreases or increases. Also, by hyper and hypothermia, the set point temperature is normal. Only the body temperature is lower than normal or higher than normal. The other slides you can read there, it is written what is the causes of hyperthermia and hypothermia and which consequences result from hyperthermia and hypothermia. You can read those. I cannot explain so much of those. Doesn't require any explanation actually. And another definition, which is important for you to know, the definition heat stroke. Heat stroke is defined as that hyperthermia by which body temperature is above 41 degrees Celsius. Also between 37 and 41, we call it hyperthermia. Above 41, we call it heat stroke. Also by heat stroke is the set point temperature normal. And heat stroke becomes very dangerous, as you see here, what can happen by this heat stroke. And the only other thing that I want to tell you about is the fever. And now by fever, the set point temperature is raised by hypothalamus. That is completely different from hyperthermia. It is the set temperature is raised by hypothalamus. Why it is raised? Because you had an infection and you had the toxins in the blood, and they go somewhere in the hypothalamus and raise the set point temperature. And now if the set point temperature is increased like this from 37, let's assume to 39, what the body should do? The body should get harder to warm up. Therefore, it tries to warm up. And slowly it warms up and reach that temperature. And this phase of warming up in the rising phase of fever, in the rising phase of fever, what is happening there? You see, because it must warm up, then what should it do with blood flow to the skin? Reduce it or increase it? Decrease, reduce it. Therefore, the skin looks pale. And it should produce more heat. Therefore, shivering. You are starting to shiver, and you perceive the situation as it is cold for you. If you feel cold and you start to shiver and you are pale, that is the rising phase of fever. Then at the falling phase of the fever, let's say you give antibiotics, the fever is gone, and then the set point temperature is returned back to 37. And now the body should cool down from 39 to 7. What happens by cooling down? Skin perfusion must increase. You have a red flash. Sweat secretion must increase. You become sweaty. And heat generation reduces, and you perceive the situation as you are warm. That is the time that you throw everything from your bed, come out and say, oh, it is warm to me. That is the falling phase of fever. And that shows you that by infections, the toxins are going, cytokines are going and changing the set point of the temperature. Not the toxin, the cytokines are mostly which go there and change the set point. Thank you very much. That is all.